Right. All right, Chemistry 3101. So where I wanted to start off with this morning was talking about what are called bond line structures. So bond line structures. And sometimes they call these skeletal structures. So we can put here AKA skeletal structures. And these are the most common, or this is the most common method of conveying the structure of an organic molecule. So if we go back to something like butane that we saw yesterday, it was one of those isomers that we were asked to draw for C4H10. Of course, there were two of them. There were butane and isobutane, so we went over that in detail. But you can see that just the time it takes me to draw this small molecule, C4H10, you might be wondering, is there a better way or an easier way to communicate the structure of this molecule? So again, this is butane. And the answer is yes. Okay, there's a few things we could do. We can condense the structure. So that means we could take the structure and we could condense it. So this would be the same as saying if you took and you got rid of all the carbon-hydrogen bonds and all the carbon-carbon bonds, which you could do as well. We'll just get rid of the carbon-hydrogen bonds, and we're going to condense this to something that looks like this. So we have CH3, CH2, CH2, CH3, and we call this a condensed structure. Now, if you're wondering, can you condense this even further? And the answer is yes, because we have these two CH2 groups that are repeating. When you have a CH2 group, it actually has a name. It's called a methylene, And when you have a CH3 group, that's got a name too. It's called a methyl group. So a methylene and a methyl. Anyhow, so you can condense those methylenes even more, and you could say CH3, and then you could have an open bracket, put CH2 for the methylene inside it, and since there are two of them, you can put 2 as a subscript here, and that will condense it even further. And so this would be a fully condensed structure. So I guess the first one would be partially condensed, and the next one would be fully condensed or more condensed, I guess. But there is an even more effective way to relate the structure of butane than this condensed structure or partially condensed structure. And that, again, is to use a bond line structure. And so the way that the bond line structure works is on the rationale that carbon always has how many bonds when it's uncharged? Who could answer that for me? How many bonds does carbon always have when it has no charge? We're not talking about carbocations or carbanions yet. Yeah, it has 4 bonds. And so if we know that carbon has 4 bonds, the way that we would relate the structure of butane is we would say, okay, well, when my pen touches the paper, you see I just made a little dot down in the left corner. That is my first carbon, and then I start drawing lines like this. So 1, 2, 3, 4. And that is the structure of butane drawn as a bond line structure. And if you're saying, well, that just looks like Charlie Brown's shirt or something, Mr. Dion, it's just a squiggle. No, what we're implying is that where the line ends, there's a carbon. So we implying that there's a carbon where the line is ending at both of the ends. And anytime there's a change in angle or a vertex, if you will, there's also a carbon there as well. Now, if we look at the 2 carbons in red, you just answered me in the chat. Everybody said carbon has 4 bonds when it's uncharged. So the atoms that we leave out, you can see, are the hydrogens. We do not include them in the bond line structure. And so it's implied that this carbon has 1, 2, 3 hydrogens attached to it, as does the other carbon in red, right? So it has 3 bonds attached to it, or 3 hydrogens. And if you look at the carbon in blue, either one of them, you see that both carbons in blue have 1, 2 bonds attached to them. You see that this one has 2 bonds attached to it, and this other blue carbon has 2 bonds. Well, what plus 2 gives you 4? And the answer is 2. And therefore, both of these carbons in blue, it is implied that they have 2 hydrogens on them. So again, where we save our time is that we don't draw in any carbons and we don't draw any hydrogens in a bond line structure. Now, somebody will usually ask me, well, Mr. Dion, the way that you drew it was this. You said, something like this. Could you draw it like this? Could you say and do that? Yes, those are the exact same thing, okay? These 2 structures that I have drawn here, these are identical to each other, okay? It doesn't matter if you zig up or down or whatever. Then I'll also have students who will ask me, okay, well, that's all well and good. Could you draw it like this? Could you say 1, 2, 3, 4 like that and draw the structure that way? The answer is yes, you can. And this these two structures, so I'll put these in a blue box, I guess. These two structures are identical. However, the reason why we prefer to draw it going up, down, up like this, or down, up, down, the reason we prefer that way is because that is actually the more stable conformation or shape of the molecule. And you'll see that clearly when we start making molecular models. And I'll try to show you a few things with molecular models as the course progresses. And so that's why we draw them as that zigzag format. So let's try another one. Let's say we had, I'll just leave that up. Let's say we had a bigger molecule. Let's say we had 1, 2, 3, 4, 5, 6 carbons like this, okay? So now we're going to have C6H14. So it's going to take me a long time to draw all these hydrogens in, which I don't like doing. And that's why I'm teaching this to you right away, so I don't have to do it anymore. So I have a total of 6 carbons. And so the way I would draw the bond line structure is that when my pen touches the paper, that's carbon number 1. So I have 1, 2, 3, 4, 5, 6. There we go. So this molecule is called hexane. Hexane. And now I've drawn the bond line structure of hexane. And if you're wondering, well, could I draw it like this? 1, 2, 3, 4, 5, 6. Yes, these two structures are completely identical to each other. Okay, they're identical to each other. You can also use bond line structures for rings. Let's say you had 6 carbons in a ring. 1, 2, 3, 4, 5, 6. That's not the prettiest ring in the world, is it? I can fix that. There we go. It's a little bit better. So let me ask you guys a question. This carbon that I have highlighted in yellow, how many hydrogens should be attached to this carbon? How many hydrogens is it missing in my structure? 2, exactly, right? You don't want to mix bond line structures and Lewis structures. So what I have drawn here, this is nothing, okay? This is pointless. This is a piece of garbage, okay? And now that's going to be on YouTube that I said that. But anyhow, that is worthless, okay? You have to draw either a complete Lewis structure or a complete bond line structure. We don't make hybrids of the two. So we put this in here, all right, like that. And then we put something like this. So here we go. So we would call this molecule, this is called cyclohexane. Anyhow, if we wanted to draw the bond line structure of cyclohexane, what's it going to look like? It's going to look like a hexagon, like this. That's all it's going to look like. Give me a thumbs up if you follow me on the rationale of bond line structures. So far, what I've shown you. Great. All right, awesome. So the only other thing I need to tell you before we get a little bit further into bond line structures is that the atoms that we leave out in bond line structures are carbon and hydrogen only. We don't leave out atoms like oxygen, nitrogen, sulfur, the halogens like chlorine, fluorine, bromine, iodine. We include those. Okay, we always include those in our bond line structure. So what would that look like? Let's say we had something like this, like dimethyl ether. Let's take diethyl ether. So let's say we have CH3CH2, oxygen, and then we have CH2CH3. Okay, this is diethyl ether. So diethyl ether. And again, the name is not important. We won't be tested on that. You don't even learn ether nomenclature until organic 2. But if we were to draw the bond line structure of this, we have the oxygen, again, that we don't leave out, and then we would have 1, 2 carbons on this side and 1, 2 carbons on this side. We do not leave heteroatoms out. So if you're wondering what's a heteroatom, these are heteroatoms. Anything that's not a carbon or a hydrogen, we call that a heteroatom. So we don't leave those out. Let's try one more, and then we'll go back into chapter 1. Let's try this molecule. This is called trimethylamine, and it looks like this if I draw a Lewis structure, or I should say a partially condensed structure. So if we draw trimethylamine, it looks like this. So if we wanted to draw the bond line structure, again, we have a nitrogen. That's a heteroatom. We don't leave that out. So we would have a nitrogen, and we would have 1, 2, 3 CH3 groups coming off of it. Also, I told you what a methylene and a methyl is. So we have 3 methyl groups coming off of it. Excuse me. And we're going to see more examples of bond line structures later today when we get into chapter 2. And you're going to see, once we look at big molecules, like an antibiotic, for example, how much easier it is to discern what's going on in the structure of the molecule when you're using a bond line structure. And it enables you to focus in on what are called the functional groups, which is also something that we're going to cover in lecture today. So functional groups and molecular representations are two big topics that we're going to cover today. Any questions about the bond line structures before we move on to section 1.13 and talk about solubility and actually look at the last few problems of question 1.12? All right, so let's go back to chapter 1. Let's see here. So, oops, that's the wrong chapter. Go back to chapter 1. And where we left off was looking at some questions that dealt with intermolecular forces. So we talked about the three most common types of intermolecular forces. So where was our first slide, right? We said the weakest of the intermolecular forces is the London force, and everything has London forces. Then we had the dipole, which is intermediate, dipole-dipole forces. And then we had hydrogen bonding, which is the strongest of all the forces. And if I can just encourage you when you're studying intermolecular forces, just be aware that intermolecular forces was covered in general chemistry. It's covered in organic chemistry, and it's never going away. Okay, it's going to be a big part of biochemistry, cell bio, all these classes. And so you want to make sure that you fully understand intermolecular forces. So again, we've covered all of the intermolecular forces in the last lecture, but we didn't finish a problem. Where was it here? We looked at the trend here with the straight chain alkanes going from butane to pentane to hexane. Then we said the more branching you have a lower surface area, so you have less surface area to come into contact. So let's take a look at these pairs of molecules and see if we can justify as to which compound is going to have a higher boiling point. So I'm going to call this compound, so we're going to start with question A. I'll call this one compound 1, and I'll call this one compound 2. Could anybody guess, or I guess give an educated guess, as to which one of these compounds is going to have the higher boiling point? Would it be 1 or 2? It's going to be compound 2, isn't it? Right. This one is going to have the higher boiling point, and it's going to be because less branching. Right. The more branching that we have, the lower the boiling point is. So compound number 2 is going to have the higher boiling point, right? If we look at compounds B, you can see that they're both cyclic compounds. So if we call this one, I'll call this one 3 and I'll call this one 4, okay? We'll keep going that way. So if I compare compound 3 and compound 4, they're both cyclic compounds. So what would we base it off of then? Which one of these is going to have a higher boiling point, do you think? And go with your gut on this one. It's going to be compound number 4, isn't it, Pablo, right? It's going to be higher boiling point, higher, I'll just put because higher molar mass. It's a higher molar mass, and if it has a higher molar mass, it's going to take more energy to convert it from the liquid state to the gaseous state, right? We're talking about boiling, which is going from a liquid to a gas, okay? Let's take a look at C. So we'll call this compound 5, and we'll call this one compound 6. So both of these compounds have the exact same molecular formula, right? Both are C4 H10O. But which one of these is going to have a higher boiling point? Would it be exactly? So it's going to be number 6. Could anybody tell me why? Yeah, I see that somebody. Thanks, Sean. Yeah, the answer is because of hydrogen bonding, right? The reason why this compound is going to have the higher boiling point, we'll put higher because of hydrogen bonding, right? Because we have a bond between oxygen and hydrogen. What's the strongest intermolecular force that's going to be found in compound 5? Could anybody tell me that? And there's no trick question or anything. We talked about this quite a bit yesterday. When you have an oxygen that has 2 bonds and 2 lone pairs, it's going to be a dipole-dipole, isn't it, Katana? Right, because it's going to have a dipole in it. Yes, so dipole, we'll just write here, dipole-dipole is the strongest force. Dipole-dipole. Okay, and what about the last one? We have 2 possibilities for hydrogen bonding, don't we? So we'll call this 7, and we'll call this one 8. You can see that I have the possibility of hydrogen bonding here, right? And then I also have the possibility of hydrogen bonding here. I see that Sean and Pablo both said it's going to be compound number 7. They're both right. Why would that be? They both have hydrogen bonding. Both have hydrogen bonding. But the first one is more linear. Exactly. Okay. We'll just put here more linearity, or more linear is fine. Or we'll put here less branching. Either way you slice it is good. All right. There you go. All righty. Let's move on. And I guess I wanted to show you one more thing here, is using our bond line structures. If we drew a bond line structure of pentane, 1, 2, 3, 4, 5, and then if we drew a bond line structure of 2-methylbutane, so that's 1, 2, 3, 4, and it would look something like this. And then we have 2,2-dimethylpropane, which would look something like this. So these are the bond line structures of these three compounds. And you can clearly see how if you had 2 molecules of pentane, you can see how easily they would interact in terms of London forces, right? There's so much surface area that comes into contact that you're going to have a lot of London forces between these two nonpolar compounds. Whereas if you have another molecule of 2-methylbutane, because you've got that methyl group sticking up, it's going to be tougher for it to interact, right? There's a bigger distance here, and so there's not going to be as strong of London forces. And you can clearly see that in the next molecule, which is 2,2-dimethylpropane, it's very difficult for those, to interact with each other. And so the London forces are going to be very limited. And that's another reason why I wanted to show you the bond line structure, because it shows you so well, it demonstrates why London forces are so much more pronounced when you have a linear compound as opposed to a branched compound. Is that cool or what? Anyhow, so let's move on to the very last section of chapter 1.13. It could be summarized by the text in red here, like dissolves like. That is an axiom that you would have learned in general chemistry. And all it means is this: like dissolves like is nothing more than if you have a polar compound, it's going to mix well or dissolve partially or maybe completely in another polar compound. So polar compounds dissolve into polar compounds, generally speaking. All right, so let's imagine you have two compounds that are capable of hydrogen bonding. Let's imagine you have this compound, CH3CH2OH. This is ethanol. So ethanol, and let's imagine you have this compound, H2O, right? And you know what that is, okay? So you can see the ethanol has the capability of hydrogen bonding, as does water. So since they both have the capability of hydrogen bonding, this is why ethanol dissolves in water, and you can make things like beer and wine and schnapps or whatever. All right, and then it says nonpolar compounds tend to dissolve in other nonpolar compounds. Well, you're just learning the subject of organic chemistry. You're probably not that familiar with many nonpolar compounds, but an example of something that would be really nonpolar that you might run into in everyday life would be something like butane in a butane lighter. So butane. And then another thing that would be really nonpolar that you would know of would be gasoline, gasoline. And these are two nonpolar compounds, so they would dissolve in each other. Not the best example I know, but they are, it is an example of two things that are nonpolar that would dissolve in each other. Excuse me. All right. Sometimes when the nursing chemistry class, we'll talk about the action of soap. And there's a little blurb in it here at the end of section 1.13. I'm sure that there's somebody here who has anybody here studied fatty acids at all? Maybe a biology class, and they teach you about triglycerides. And then, if a fatty acid undergoes beta oxidation in the Krebs cycle, right? And you extract all that energy in the electron transport chain and whatnot. Well, if you've ever wondered what a fatty acid is, so a fatty acid is nothing more than this. If you have this kind of group here, we call this a carboxylic acid. And then if you have a really long tail, so I'm going to break the rules here and mix a bond line structure with a Lewis structure. So if you have a really long nonpolar tail like this, so this is all carbon and hydrogen, right? So this is going to be completely nonpolar. And then if you have a polar group at the front, like this one here, it's got a dipole in it. And so this is polar. We call this a fatty acid. So if you're wondering, well, what's the difference between what you've drawn and what's drawn here? Well, you can see that mine doesn't have a negative charge and theirs does. So what happens is when you hydrolyze fat in base, it creates a fatty acid salt, if you will. And so you end up with a negative charge on this oxygen here. And so this is the structure of soap. So if you've ever washed your hands before, which I recommend doing, with Irish Spring or Ivory soap or Dove, if you're a high roller or something like that, what you're doing is you're just using fatty acids in the salt form of a fatty acid to wash your hands. So if you're wondering, well, how does that work? Well, here's how it works. So that this, what we have drawn here, you see how they made the front part green and then they made the whole tail kind of red or brown or whatever. That is what's being shown right here. So here's the green head portion, and then this would be the hydrophobic tail sticking down in here. So you can see there's hundreds of thousands of these molecules, of these fatty acids, and what they do is that they surround dirt. So what we have in the middle here, this is grease or dirt or maybe a piece of earwax or something. Okay, anyhow, and then we have the soap molecule. So this is soap. Okay, so we have our polar portion, right? This part is polar, and the interior is non-polar, and that's a good thing because grease and dirt, oils that we get on our hands, those are non-polar, and so the non-polar tails gather around the dirt or grease on our hands or whatever, and they surround it, and then the polar head groups are facing on the outside, and then it's in an aqueous environment where you're, in the shower or washing your hands in the sink or something like that. And so the water is going to wash the micelle. We call this a micelle. It's going to wash it down the drain. And so now you know a little bit about how soap works. And I don't have time to go into fatty acids and in detail and triglycerides and how the pioneers made soap and all that kind of stuff, but it's something kind of interesting that you might want to look into. Anyhow, so there you go. You've just finished your first chapter in Chemistry 3101.